Hello everyone, welcome back to Chemarcom. Today we are going to continue selenium dioxide reagent basics and their application in part 2. If you are new to the channel, don't forget to subscribe. So in our first part 1 video, we already seen that selenium dioxide preparation properties, and one of the important application is allylic or benzylic oxidation. So today we are going to see three more important applications such as oxidation of carbonyl compounds, oxidation of alkynes, and dehydrogenation reaction. Let's see one by one. First, moving on oxidation of carbonyl compounds. Let's consider this example. Here you see this alpha carbonyl compounds having this alpha position, having methyl or methylene group. When you use selenium dioxide, which quickly oxidize this position into corresponding carbonyl compound product. So especially this type of reaction is called Rayleigh oxidation reaction. When you come to the mechanism, there are two mechanisms can useful for explain the oxidation reaction. So first one is Corey mechanism, another one is a Sharpless mechanism. So first you'll see about the Corey mechanism. We already know that when you take the ionizable ketone that may exist in the ketoenol tautomerism, here you see this is the enolic form of that corresponding ketone compound. So which readily react with selenium dioxide. Here you see this oxygen has two lone pair of electron, one of its electrons which readily attack the selenium atom, then followed by this pi electron move towards to the oxygen atom, then followed by pick up this hydrogen atom which produce this corresponding intermediate. So now you see this pi electron readily attack this carbon, then followed by this pi electron move towards to this here, this center, then followed by oxygen selenium bond cleavage happen to produce this corresponding intermediate. So now you see after the formation of this intermediate, so here you see this carbon hydrogen bond cleave, this electron move towards to this center, then followed by oxygen selenium bond cleavage happen, then this electron moves towards selenium atom, which then kick off hydroxy group, which leads to generate corresponding diketone compound as well as selenium and water as a byproduct. So particularly this mechanism is called Corey's mechanism. Let's moving on Sharpless mechanism. So instead of attacking this hydroxy group, it attacks this carbon enolic position. That's called Sharpless mechanism. Here you see this carbon attacks selenium center, then followed by this pi electron moves towards to the oxygen center, which then readily takes the hydrogen abstraction from this position, which leads to generate this corresponding intermediate. So which then here you see, which then readily kick off water molecule to produce this corresponding intermediate. So after the formation of intermediate, which readily react with water molecule, here you see how this happened. This oxygen has two lone pair of electron, which readily attacks this center, then followed by this pi electron move towards to the selenium atom. Then this pi electron readily takes the one of the hydrogen atom, which produce this corresponding intermediate. So now you see this electron moves here, then followed by this one, this carbon selenium bond cleavage happened. This electron moved towards the selenium atom, then followed by kick off hydroxy group, which produce this corresponding ketone, diketone product, as well as selenium and water as a byproduct. So particularly this mechanism is called Sharpless mechanism. Therefore, we can use either Corey mechanism or Sharpless mechanism in order to explain the formation of this corresponding diketone product. So let's see some of the examples based on alpha carbonyl compound oxidation. Here you see when you take the acetaldehyde, when you use selenium dioxide, which readily oxidize this methyl group, which produce this corresponding aldehyde product. So this is one of the interesting example. Here you see this compound having methyl group as well as methylene group. Therefore, when you use selenium dioxide, which group will get oxidized? So when you get this type of situation, you just see, just to put the ketoenol tautomerism product. Here you see, so when you enolize this methylene position, you will get this enol form, and similarly, when you get enolize this position, you will get this enolic form. So according to this enolic form is more stable when compared to this one, And simply you just see more substituted alkene is highly stable when compared to the less substituted alkene. Therefore, this form only quickly react with selenium dioxide, which readily produce this corresponding product. Therefore, we can roughly say CH2 group is, methylene group is more reactive compared to the methyl group. Let's see some more examples. So here you see cyclohexanone. When you take the selenium dioxide, which readily produce corresponding cyclohexadione product. So this is another one important example. When you use selenium dioxide, now you closely look this compound. Here also methylene group, as well as here also methylene group. However, this methylene group somewhat sterically hindered with near having one methyl group. Therefore, when you use selenium dioxide, which readily oxidize this position, less hindered position, which produce this corresponding diketone product. So this is another interesting example. When you use selenium dioxide, here you see this one is a methylene group. Now you see this compound having two allylic site. However, this methylene group only oxidize when you use selenium dioxide to produce this corresponding diketone product. So this is another interesting problem. So now you look, here also methylene group, here also methylene group, but this methylene group near to phenyl group, that means benzylic group. Therefore, when you use selenium dioxide, this position is more reactive, which readily oxidize to produce this corresponding ketone product. So just like monoketone, so if you take the 1,3 diketone, this also can oxidize when you use selenium dioxide, which produce this corresponding ketone product. And similarly, when you take the indane dione, when you use selenium dioxide, which readily produce corresponding trione product, this product is somewhat unstable, which readily react with water to produce corresponding nitrite product. So next we moving on oxidation of alkynes. So when you come to the oxidation of alkanes, only two examples only known in the textbook. So one of the example is when you take the internal alkyne, when you use selenium dioxide and sulfuric acid, which readily produce corresponding carbonyl compound. When you think about the mechanism, we already know that when you take the any alkyne, when you use sulfuric acid and water, which readily produce corresponding ionizable ketone as a product. Once if you get the ionizable ketone product, that might undergo selenium dioxide oxidation reaction, just like we discussed in the previous slide, which readily oxidize to produce this corresponding dicarbonyl compound. And similarly, when you take the terminal alkyne, which produce corresponding glyoxylic acid derivatives. Next, we moving on dehydrogenation reaction. When you take the 1,4 dicarbonyl compound, when you use selenium dioxide under 170 degrees Celsius, which readily undergo dehydrogenation reaction to produce this corresponding alkene product. Just like our alpha carbonyl compound oxidation reaction by selenium dioxide, here also there are several mechanisms known to explain the formation of corresponding alkene product. So this one is one of the latest mechanism to explain how this dehydrogenation reaction takes place when you use selenium dioxide. So here you see when you use selenium dioxide, so this pi electron readily abstract this proton, this electron move towards here, then followed by this pi electron readily attack the selenium atom, which readily produce this corresponding intermediate. We can redraw this intermediate like this. So now you see this pi electron readily pick up this electron shifted here, then followed by this electron shifted here. So which leads to cleavage of carbon selenium bond, which produce this corresponding alkene product by 1,4 elimination reaction. So let's see some of the example. So here you see 1,4 dicarbonyl compound when you use selenium dioxide, which produce corresponding alkene product. And similarly, when you having some benzylic group also, which readily undergo selenium dioxide dehydrogenation reaction to produce corresponding alkene product. And similarly, when you take the 2 acetic acid molecule, when you use selenium dioxide, which readily produce corresponding succinic acid compounds. So apart from these three applications, selenium dioxide also possible to utilize as a catalyst for some of the reaction. Here you see one of the reaction. When you take the maleic acid, when you use selenium dioxide and hydrogen peroxide reagent, here you see selenium dioxide act as a catalyst, which readily produces this corresponding dihydroxylation product as a racemic compound. And similarly, when you take the fumaric acid, when you use selenium dioxide and hydrogen peroxide, which readily produce meso dicarboxylic acid as a product. In both cases, dihydroxylation takes place. Let's see how this happened by magnetically. Selenium dioxide and water which readily produce corresponding selenous acid. The selenous acid readily react with hydrogen peroxide which produce corresponding reactive species. This reactive species readily react with alkene to produce this corresponding epoxy product. That epoxide readily react with water to produce corresponding trans dihydroxylation product. So based on that, we can get the either racemic product or meso product when you use appropriate corresponding alkene compounds. So today we discussed 3 important applications of selenium dioxide. I hope this video has expanded your knowledge on selenium dioxide reagent in organic synthesis. If you enjoy this video, just like, share and comment. As well as if you are new to this channel, don't forget to subscribe. Here are some of the practice problems. When you get the free time, you just give it a try. So until next time, bye bye.